Tonight, we're going to look at a picture that you have almost certainly seen. The solar system viewed from above, the sun glowing at the center. Mercury, Venus, Earth, and Mars tracing their tight inner circles. Then the wider rings of Jupiter, Saturn, Uranus, and Neptune spreading outward like ripples on a still pond. You've seen this image in textbooks, in planetarium shows, in every documentary that has ever tried to explain where we live. Here's what most people don't realize. That picture is not a photograph. No human being has ever seen the solar system from above. No camera, launched by any nation at any point in the history of spaceflight, has ever turned around and taken that picture. Every single image you have ever seen of our own solar system, viewed from a vantage point looking straight down at it, is a mathematical reconstruction. A drawing. An extraordinarily precise, computer-generated guess built from data gathered entirely from within the plane of the planets themselves, never from above it. And this isn't because nobody has thought to try. It's not a funding problem, or a patience problem, or a failure of ambition. It turns out that going up, straight up, out of the flat disk that every planet, moon, and asteroid in our solar system obediently orbits within, might be one of the single hardest things to do anywhere in space. Harder, in some very real mathematical ways, than reaching Mars. Harder than reaching Pluto. Harder, per unit of distance traveled, than almost anything else humanity has ever attempted to launch. The first surprise is that up doesn't actually mean anything, cosmically, until you very carefully define what you're asking it to mean. The second surprise is a piece of physics so unforgiving that changing your direction in space, even by a modest angle, can cost more fuel than the entire journey that got you into space in the first place. The third surprise is that exactly one spacecraft in the entire history of human spaceflight has ever actually managed to escape the flat plane of the solar system and look back at it from a genuinely different angle. And it did so using a trick that had nothing to do with rocket engines at all. And the fourth surprise, the one that should genuinely stop you, is this. Even that one spacecraft, having achieved what no other mission ever has, never took the picture. It couldn't. It wasn't built to. Which means the most familiar image of our own home, the one every science class has shown you, remains, to this day, something no eye and no lens has ever actually witnessed. By the end of tonight, you're going to understand exactly why going up in the solar system is so profoundly difficult, what it actually took for the one spacecraft that managed it, and why the most famous picture of our own cosmic neighborhood is also, quietly, the most imagined one. Before we dive in, if you're someone who finds real comfort in understanding the true structure of the place we live, who trades the noise of the day for a little cosmic perspective before sleep, consider liking this video or subscribing to the channel. It's a small thing, but it helps us keep making this kind of content for people who share that same quiet curiosity. Now, let's begin. Let's start close to home, because before we can understand why going up in the solar system is so difficult, we need to understand why up itself is such a slippery idea in space at all. Gravity does not switch off in orbit. This is one of the most persistently misunderstood facts about spaceflight, and it's worth stating plainly, because everything else tonight depends on getting it right. The International Space Station orbits at roughly 400 kilometers above Earth's surface, and at that altitude, gravity is still pulling on the station and everyone inside it at approximately 88 to 90% of the strength it exerts down here, on the ground, right now, on you. Astronauts aboard the ISS are not floating because gravity has disappeared. They are floating because they, and the station around them, and everything inside it, are all falling, continuously, together, around the entire planet. NASA describes this precisely as a state of continuous free fall. The station moves tangentially at roughly 7.66 kilometers per second, fast enough that, as it falls toward Earth, The curve of its fall exactly matches the curve of the Earth falling away beneath it. It is always falling, and it is always missing. That perpetual, graceful miss is what an orbit actually is, and the sensation this produces. The absence of any felt weight, despite gravity still being almost entirely present, is what we colloquially, and somewhat misleadingly, call zero-G. Because free fall removes the felt weight of the human body, something deeper starts to unravel almost immediately. The body's own internal sense of direction. Buried in your inner ear are tiny structures called otolith organs, microscopic crystals of calcium carbonate resting on beds of gravity-sensitive hair cells that under ordinary Earth gravity settle in a consistent, predictable direction and tell your brain, constantly and automatically, which way is down. In free fall, those crystals stop settling anywhere in particular. They drift. And the signal your brain has relied on for your entire life, every waking moment since infancy, simply stops arriving in any coherent form. Peer-reviewed studies of returning astronauts document the aftermath of this in remarkably consistent detail. Exaggerated perceived motion, tumbling illusions, genuine postural instability, sometimes persisting for days after landing back on solid ground. NASA has a specific name for the disorientation that happens on the way up into orbit, too. Space adaptation syndrome. Typically resolving somewhere between 2 and 4 days after reaching space, as the brain slowly, grudgingly, learns to stop trusting a sense that no longer means anything. Astronauts across 5 decades of spaceflight describe the resulting shift in almost identical language, regardless of nationality, regardless of era. After roughly 48 hours in orbit, a wall becomes a floor becomes a ceiling. The entire idea that the room has an orientation quietly, completely dissolves. Inside the International Space Station today, directions aren't named up and down at all. They're named by module: forward, aft, starboard. The same vocabulary you'd use aboard a ship, because up and down have simply stopped being useful words. Now extend that same logic outward from the space station to the entire solar system. Standing on Earth, up points directly away from Earth's center. A specific, local, gravity-defined direction that only makes sense because you happen to be standing on Earth. Standing on Mars, up points away from Mars's center instead. A completely different direction in absolute space, defined entirely by whichever planet happens to be beneath your boots. On a spacecraft drifting quietly between planets, with no single nearby mass dominant enough to define a clear vertical, the entire concept simply stops applying in any strong sense. Cosmically, up and down are always parochial. They are labels we borrow, temporarily, from whichever gravitational body we happen to be closest to at the time. There is no universal up painted across the sky, waiting to be discovered. There is only ever a local one, and it changes completely, depending on where you're currently standing. This matters enormously for tonight's story, because the question we're actually going to explore, why it's impossible to go up in the solar system, needs, first, an honest, working definition of what up could even mean at that scale. And to find that definition, we need to understand something that happened 4.6 billion years ago, long before Earth, or gravity's local pull on your body, or even the sun itself, existed in anything like their current forms. Here is the reason nothing in our solar system orbits randomly, sideways, at some arbitrary angle. The reason Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune all travel around the Sun within the same narrow, shared band of space, rather than scattering in every direction like buckshot. It traces back roughly 4.6 billion years to a single, slowly rotating cloud of interstellar gas and dust, vast, diffuse, and almost imperceptibly spinning. As gravity pulled that cloud inward on itself, something inevitable happened. Conservation of angular momentum, one of the most stubborn laws in all of physics, forced the collapsing cloud to spin faster and faster as it shrank. The classic image is a figure skater pulling her arms in during a spin. The same total rotational momentum, concentrated into a smaller space, has to spin faster to conserve itself. Picture a diffuse, hand-sized wisp of interstellar cloud gradually tightening down into a spinning saucer roughly the size of a dinner plate. And because that collapsing cloud was rotating, gas couldn't fall freely toward the newly forming star along every possible direction. Along the spin axis, straight toward what would become the star's poles. Material could fall in relatively unobstructed. But perpendicular to that axis, centrifugal effects from the spin itself actively resisted the collapse. Material trying to fall straight in from the sides simply couldn't, fast enough, without first losing its excess spin. The material that did manage to fall in along the poles either landed on the forming star directly or was flung back out entirely. Everything else, the vast majority of the cloud's original material, settled instead into a broad, comparatively thin, rotating equatorial disk. Astronomers call this the protoplanetary disk, and it is where every planet in our solar system, without exception, was eventually born. We are no longer forced to imagine this process purely through theory. In 2014, the LMA radio telescope array captured a direct image of exactly this kind of disk, surrounding a young star called HL Tauri, a system only about 1 million years old, essentially a newborn by stellar standards. The image is genuinely striking. A razor-thin ring structure, seen at an inclination of 47 degrees to our line of sight, with sharply carved dark gaps already visible where young, still-forming planets are actively sweeping up material along their own orbital paths. We are looking, in that single photograph, at something very close to a baby picture of our own solar system, captured mid-formation, around a completely different star. Here's a sensory way to hold the actual proportions in mind. Detailed models of protoplanetary disks find an aspect ratio, height compared to radius, of roughly 0.05 at distances comparable to Earth's own orbit. In plain terms, the disk is roughly 20 times wider than it is thick. If you imagine the disk that eventually formed our entire solar system scaled down to the size of a large pizza, spanning about 40 centimeters across, it would be thinner at its outer edge than the pizza's own crust. A saucer of material barely a centimeter thick, at most, stretched across an enormous circular span. Everything that later condensed out of that thin, spinning disk. Mercury, Earth, Jupiter, Neptune, every planet, and most of the large moons orbiting them, inherited its flatness directly. The 4 giant planets in particular carry an overwhelming share of the entire solar system's total angular momentum. Jupiter alone contributes 60.3%, Saturn 24.5%, Neptune 7.9%, and Uranus 5.3%. Added together, that's 98% of everything, concentrated in just 4 worlds. Their combined orbital motion defines what astronomers call the invariable plane, the single most accurate mathematical description of the solar system's true, average orbital plane that exists. Every other object, every smaller planet, every moon, every asteroid, is simply a small perturbation, wobbling gently around that dominant, shared plane. Measured against that invariable plane, the giant planets themselves are almost eerily flat. Jupiter tilted just 0.32 degrees, Saturn 0.93, Uranus 1.02, Neptune 0.72. Even Earth, measured against the true invariable plane rather than against its own orbit, which by definition sits at exactly 0, sits within a couple of degrees of that same shared plane. Only the smaller, more distant bodies drift further. Mercury at 7.01 degrees, and Pluto, well beyond the 8 major planets entirely, tilted at a considerably more dramatic 17.14 degrees. A genuine outlier, hinting at a more chaotic, less orderly history than the planets that formed closer to the disk's densest, most orderly interior. This is the shape we actually live inside, not a sphere of orbits scattered randomly through space in every direction, the way popular imagination sometimes pictures a solar system, a disk. Startlingly, almost impossibly thin relative to how wide it is. And every spacecraft ever launched from Earth begins its journey already trapped inside that same flat plane before a single engine has even fired. Now we can finally give up a real, working definition, the only one that actually carries physical meaning at the scale of an entire solar system. Going up in this precise sense means deliberately leaving the ecliptic, the plane defined by Earth's own orbit around the Sun, so named specifically because eclipses can only occur when the Sun, Earth, and Moon happen to align within it. The ecliptic sits just 1.57 degrees off from the solar system's true invariable plane, close enough that, for our purposes tonight, we can treat them as functionally the same shared disk. Going up means pointing a spacecraft's trajectory away from that disk entirely, toward the Sun's own North Pole or its South Pole, rather than toward any of the other planets, all of which, conveniently and unsurprisingly, sit almost exactly where you'd expect them to, within that same shared plane. Here is the fact that should genuinely stop you, because it's the kind of thing that sounds like it can't possibly be true, and yet it is, precisely and completely. Of every spacecraft humanity has ever launched, every single Mars rover carrier, every mission to Venus, every probe sent to Jupiter or Saturn or the icy edges of the solar system, all the way out to the twin Voyagers and New Horizons, every single one of them was deliberately designed to stay close to the ecliptic, because that is where the destinations are. Planets don't wander off the disk. Neither, generally, do the missions built to visit them. Even Voyager 1, our most distant spacecraft, now farther from Earth than any human-made object has ever travelled, only drifts about 35 degrees north of the ecliptic today. And that angle wasn't chosen deliberately as some grand design decision to escape the plane. It's simply a residual consequence of the specific flyby geometry required to visit Saturn's moon Titan decades ago on its way outward. A side effect of an entirely different goal, not an intentional departure from the plane at all. Out of every mission ever launched in the entire history of spaceflight, on any nation's rockets, for any purpose whatsoever, exactly one spacecraft was designed, from its very first blueprint, specifically to leave that plane. It is called Ulysses. It launched in 1990, and we are going to spend real time with its story tonight, because what it took to send even that one spacecraft up reveals, more clearly than almost anything else in modern spaceflight, exactly how strange and unforgiving the physics of changing direction in space actually turns out to be. Picture, for a moment, every object humanity has ever launched into deep space as a single dust mote, caught and illuminated inside one narrow shaft of sunlight streaming through a window. Some of those motes drift outward, away from the light source. Some drift inward toward it. Some circle lazily within the beam itself. But virtually all of them, without exception, stay inside that same narrow shaft of light. Only one small mote, once, in the entire history of the room, ever tumbled sideways and drifted genuinely out of it. This is shocking discovery number one. Up in the solar system is not merely an unusual direction to travel. It is a direction that humanity, across more than 60 years of continuous spaceflight, across hundreds of successful missions to every corner of our cosmic neighborhood, has attempted exactly once. To understand why up is so difficult, and why it took something as unusual as Ulysses to even attempt it, we need to understand a fact about rocket launches that almost never gets mentioned, because it's so easy to overlook. Nothing launched from Earth ever actually starts from rest. Before a single engine ignites, before a rocket has cleared its own launch tower, it is already moving. Earth itself orbits the Sun at a mean velocity of 29.78 kilometers per second, ranging from 30.29 kilometers per second at perihelion, when Earth is closest to the Sun, down to 29.29 at aphelion, when it's farthest. That works out to roughly 107,208 kilometers per hour, something in the neighborhood of 67,000 miles per hour. Fast enough that Earth covers its own entire diameter in about 7 minutes and crosses the full distance to the Moon in roughly 4 hours. Every rocket sitting on a launch pad anywhere on the planet, in Florida, in Kazakhstan, in French Guiana, inherits this entire velocity automatically, simply by virtue of sitting on a planet that's already moving that fast. And critically, every single component of that inherited velocity lies precisely, exactly, within the ecliptic plane. Earth's rotation adds only a comparatively small amount on top of this, roughly 0.46 kilometers per second at the equator from the planet's own daily spin, a genuinely minor contribution next to the enormous orbital velocity already baked into the launch. Here's a way to actually feel the scale of that inherited motion, because 29.78 kilometers per second tends to slide past most people without registering. In the time it takes to say, slowly, out loud, 1 Mississippi, about 1 second, Earth has already traveled roughly 30 kilometers along its orbit, roughly the length of the island of Manhattan. In the length of one ordinary, unhurried breath, Earth has covered something closer to 90 kilometers, more than the width of an entire small US state. And every rocket launched from Earth's surface begins its own journey already carrying that same staggering velocity before its own engines have contributed a single additional meter per second. A rocket's own delta V budget, the total velocity change its engines are actually capable of providing, is, relatively speaking, a modest addition layered on top of all that inherited motion. The Saturn V, the most powerful rocket ever successfully flown to carry humans, had a total delta V capability of roughly 18 kilometers per second. A Falcon Heavy, flown in fully expendable mode, delivers something in a similar range. Even the extraordinarily powerful inertial upper stage that eventually flung Ulysses out of low Earth orbit only added about 15.4 kilometers per second of heliocentric escape velocity. A genuinely remarkable figure, noteworthy specifically because, at the time, it represented the highest speed any human-made object had ever achieved. But here is the detail that turns out to be the entire crux of tonight's story, the specific, unavoidable physical root of the whole problem. That 15.4 kilometers per second Ulysses gained wasn't added in some independent direction of its own choosing. It was added within Earth's own reference frame, meaning it stacked directly on top of Earth's already existing 29.78 kilometers per second of ecliptic plane velocity. It didn't cancel that inherited sideways motion. It couldn't. Physics doesn't allow one velocity to simply erase another by adding more speed in a different direction. Velocities combine as vectors, and the original sideways component remains, stubbornly, embedded in the spacecraft's total motion, no matter what else gets added to it. To send a spacecraft genuinely vertical out of the plane entirely, you cannot simply point your engines a different way and fire. You would first need to essentially unwind that entire 30 kilometers per second of inherited sideways motion, cancel it out, effectively bringing the spacecraft's ecliptic plane velocity back towards zero, and only then spend additional fuel accelerating it in the genuinely new, perpendicular direction you actually wanted to travel in. 2 full, expensive maneuvers stacked on top of each other, just to change direction rather than simply going faster or farther. This is the physical root of why up is so hard. Not a lack of powerful enough engines, not a lack of ambition. A specific, unavoidable, inherited velocity, 29.78 kilometers per second, gifted to every single object ever launched from Earth, entirely within the ecliptic plane. That has to be actively fought against, rather than simply built upon if you ever hope to travel in a genuinely different direction. Now let's put real numbers on exactly how expensive fighting that inherited velocity actually turns out to be. Because once you see these two equations working together, the impossibility of casually going up in the solar system stops being an abstract claim and becomes something closer to an obvious, inescapable conclusion. The first equation is called the Tsiolkovsky rocket equation, and rocket engineers sometimes refer to it, with a certain amount of genuine dread, as the tyranny of the rocket equation. It states that to change your velocity by some desired amount, called delta V, the ratio between your fully fueled mass and your empty mass has to equal E, the mathematical constant, raised to the power of your desired delta V divided by your engine's exhaust velocity. That relationship is exponential, not linear. And exponential relationships have an uncomfortable habit of turning modest-sounding requirements into wildly impractical ones extremely quickly. Here's a concrete sense of the tyranny in action. A typical chemical rocket has an exhaust velocity around 4,500 meters per second. Reaching low Earth orbit from the ground requires roughly 9.7 kilometers per second of total delta V. Run those two numbers through Tsiolkovsky's equation, and an idealized single-stage rocket attempting that journey needs to be 88.4% fuel by total mass just to make it to orbit at all. And here's the truly unforgiving part. Double the required delta V, and you don't simply double the fuel you need. You square the entire mass ratio. The exponential doesn't play fair. The second equation is specifically about changing your orbital plane, and it's arguably even less forgiving than the first. If you want to tilt your orbital plane by some angle, without changing your overall speed, the delta V required works out to 2 times your current velocity, multiplied by the sine of half your desired angle change. Notice something important about what that equation does not contain. It has no dependence whatsoever on how much fuel you happen to be carrying, only on how fast you're already moving and how large an angle you're trying to rotate through. And at large angles, it becomes genuinely, brutally expensive. Let's walk through the actual numbers slowly, because they escalate in a way that's worth sitting with. In low Earth orbit, typical orbital velocity is about 7.5 kilometers per second. To tilt that orbit by 10 degrees costs roughly 1.31 kilometers per second of delta V. Genuinely manageable, comparable to a launch abort maneuver. Tilt it by 24 degrees, and the cost jumps to roughly 3.13 kilometers per second, which happens to be almost exactly the same amount of delta V it would take to escape Earth's gravity entirely from that same orbit. Tilt it by 60 degrees, and the cost reaches a full 7.5 kilometers per second, an entire orbital velocity's worth of fuel, essentially dumped as waste heat, simply to rotate your direction of travel. And tilt it by a full 90 degrees, and the cost climbs to roughly 10.6 kilometers per second, more delta V than it took to reach orbit from the ground in the first place. Now apply this same unforgiving formula to Earth's own inherited orbital velocity, that 29.78 kilometers per second every rocket launches with, already built into the ecliptic plane. A full 90-degree flip out of the plane entirely and up toward the sun's pole requires approximately 42 kilometers per second of delta V. Run that number through the Tsiolkovsky equation, using a good chemical rocket with an exhaust velocity around 4,400 meters per second, and the required mass ratio comes out to roughly E raised to the power of 9.5, somewhere in the neighborhood of 15,000. For every single kilogram of spacecraft you actually want to deliver out of the plane, you would need approximately 15 tons of fuel. And that fuel needs its own tanks. Those tanks need their own structural mass, which needs its own fuel to lift in an exponential cascade that closes in on itself almost immediately, well before it ever produces a workable mission design. Picture driving a car at full highway speed and attempting a perfect 90-degree turn instantly without ever slowing down first. You cannot do it. Physically, mechanically, it simply isn't possible. You would first need to bring the car to a complete stop, and only then accelerate again from scratch in the entirely new direction. And in the vacuum of space, that initial slowing down doesn't come free the way easing off a gas pedal does on Earth. There's no road surface to push against, no friction to bleed off unwanted velocity. Every single bit of deceleration costs exactly as much fuel as the original acceleration did, in the first place, to build that speed up. This is shocking discovery number 2. Changing your direction in space, especially by a large angle, can be dramatically more expensive in raw fuel terms than simply traveling farther or faster ever would be. A 90-degree plane change from Earth's own orbital velocity costs more delta V than launching to orbit in the first place. Fully unwinding Earth's inherited 30 kilometers per second just to point straight up would require a mass ratio so extreme that no rocket ever built or seriously proposed could plausibly carry it. This is precisely the wall that stood in the way of ever sending a spacecraft directly up using brute force propulsion alone. And it's exactly the wall that one single mission, decades ago, had to find an entirely different way around. Before we get to the spacecraft that actually solved this problem, it's worth sitting for a moment with exactly why brute force propulsion was never a realistic option in the first place. Because the scale of the impossibility is easy to state as a number, but harder to genuinely feel. Real mission designers do have some tricks available to soften the plane change formula somewhat. One common technique involves first raising a spacecraft's orbit out to a very high, distant point. It's a aphelion, where its overall orbital velocity naturally slows down considerably, simply because objects moving farther from a central mass travel more slowly along their orbits. Performing the plane change maneuver at that distant, slow-moving point, rather than close in where velocities are high, meaningfully reduces the delta V the maneuver actually costs, since the formula depends directly on your current velocity at the moment of the burn. Afterward, the spacecraft can drop back down into a more useful, closer orbit, now carrying its new inclination with it. These techniques genuinely help. They're a standard part of how real missions are planned, and they've meaningfully reduced the cost of smaller plane changes on numerous real spacecraft. But even the cleverest combination of these tricks cannot rescue a mission attempting a full, direct propulsion journey out of the ecliptic entirely. The fundamental problem, that inherited 29.78 kilometers per second, locked permanently within the plane, that has to be substantially unwound before any genuinely new direction becomes achievable, simply doesn't go away. It can be softened at the margins. It cannot be eliminated. This is precisely why, when mission planners in the 1970s and 1980s first began seriously designing a mission to study the sun's poles, direct propulsion was ruled out almost immediately. The engineering assessment at the time was blunt. Tilting a spacecraft's orbit to the roughly 80 degrees required to reach a genuinely useful solar polar vantage point would demand, in the analysis's own words, a large change in heliocentric velocity, the energy to achieve which far exceeded the capabilities of any launch vehicle. No rocket, then or now, could simply power its way up. If humanity was ever going to see the sun's poles directly, or, as an eventual side effect, get anywhere close to a genuine bird's eye vantage on the solar system's own flat disk, it was going to require an entirely different kind of trick. Not a bigger engine, a borrowed one. If a rocket alone could never generate enough delta V to leave the ecliptic plane, the only remaining option was to borrow that energy from somewhere else entirely. And the only object in the solar system with anywhere near enough spare energy to lend was Jupiter itself. The mission that pulled this off is called Ulysses, a joint mission between the European Space Agency and NASA, launched on October 6, 1990, at 114716 UTC, carried into orbit aboard the Space Shuttle Discovery, and then boosted further outward by a combination inertial upper stage and PAM-S rocket motor. The spacecraft itself was small, a total launch mass of just 371 kilograms, of which only 55 kilograms was scientific payload. Power came from a single GPHS radioisotope thermoelectric generator, producing about 285 watts. enough, roughly, to run a couple of household appliances, sustaining a spacecraft that would go on to operate for the better part of 2 decades in one of the most demanding environments in the solar system. Ulysses could not fly directly toward the sun's poles. No rocket could give it the delta V that would require. Instead, mission planners sent it outward first, on a long, patient trajectory toward Jupiter, deliberately using the giant planet not as a destination, but as a tool. On February 8, 1992, Ulysses swept past Jupiter at a distance of roughly 378,400 kilometers, and the encounter was not gentle. Jupiter's immense gravity seized the spacecraft's trajectory and bent it violently, first curving it below the plane of the ecliptic entirely, and then flinging it back inward toward the Sun on an almost fully polar orbit, tilted roughly 80 degrees to the plane every other spacecraft in history had stayed close to. In a single flyby, using nothing but Jupiter's own gravity, Ulysses achieved what would have required somewhere in the neighborhood of 30 kilometers per second of delta V to accomplish through propulsion alone, an amount no chemical rocket, then or now, could plausibly have supplied. For nearly 18.5 years afterward, more than 4 times its originally planned design life, Ulysses swept in long, looping arcs high above and far below the Sun, completing 3 full polar orbits, each pass over the poles gathering measurements that no other spacecraft, before or since, has ever directly obtained. On September 13, 1994, at a distance of 2.3 astronomical units from the Sun, Ulysses reached a maximum solar latitude of 80.2 degrees south. The following year, it reached the same 80.2 degrees, this time north, becoming and remaining the only spacecraft in history to have directly sampled the environment above both of the Sun's poles. What it found, across those repeated polar passes, genuinely reshaped scientists' understanding of our own star. The fast solar wind streaming outward from the Sun's polar coronal holes moves at a remarkably steady 750 kilometers per second, roughly twice the speed of the slower, more turbulent wind that dominates near the ecliptic plane, closer to 400 kilometers per second. The Sun's polar magnetic field turned out to be substantially weaker than pre-mission models had predicted, and it continued weakening progressively across the entire span of the mission. The solar wind's overall strength itself declined steadily throughout Ulysses' operational lifetime, eventually reaching a 50-year low by 2008. Because the mission lasted long enough to observe both poles at opposite phases of the Sun's roughly 11-year magnetic cycle, Ulysses directly captured the Sun's global magnetic field in the act of completely reversing itself. A genuinely rare, longitudinal view no shorter mission could ever have achieved. It found that interstellar dust, drifting continuously into our solar system from deep space beyond it, is roughly 30 times more abundant than pre-mission estimates had assumed. And in May 1996, entirely by chance, Ulysses flew directly through the tail of Comet Hyakutake, at an enormous distance from the comet's own visible nucleus, revealing, unexpectedly, that cometary tails extend dramatically farther through space than anyone had previously imagined possible. Ulysses was deactivated on June 30th, 2009. Its radioisotope power finally too depleted to continue useful operations, having outlasted its planned mission by more than a factor of 4. There is one more detail about Ulysses worth sitting with directly, and it's the detail that carries us into the heart of tonight's story. Ulysses carried no camera. Not a small one. Not a low-resolution one. None at all. Its entire 55 kilograms of scientific instruments were built to feel the space around it. Plasma sensors, magnetometers, particle detectors, a dust experiment, rather than to photograph anything. The one spacecraft in human history that ever genuinely escaped the flat plane of the solar system and looked back at it from a vantage point no other mission has ever occupied, never once turned around to take a picture. Here is the sentence that deserves to sit with you for the rest of tonight, because once you understand everything we've covered so far, its full weight becomes genuinely clear. No human being and no human-made camera has ever seen the solar system from above, every schoolbook image. The neat concentric ellipses of Mercury through Neptune, viewed from some elevated vantage point in space, the sun glowing bright at the center, the planets strung out like beads along invisible wires, is a construction. It is built entirely from ephemerides, precise mathematical models of the planet's orbits, calculated from measurements gathered exclusively from within the plane itself, and then extrapolated outward using Newton's laws and centuries of refined celestial mechanics. It is not, and has never been, an actual photograph taken from an actual camera occupying an actual position above the disk. The reason traces directly back to everything we've just walked through. To photograph the ecliptic plane genuinely face-on, from a useful vantage point, say 30 astronomical units directly above it, far enough out to frame the entire planetary system in a single wide shot. A spacecraft would first need to substantially cancel Earth's inherited 29.78 kilometers per second of ecliptic plane velocity, and then accelerate, from there, perpendicular to it, fast enough to actually arrive somewhere useful within a human lifetime. No rocket ever built comes remotely close to making that combination possible. Ulysses reached precisely the right kind of vantage point, 80.2 degrees above the sun's own equator, a genuinely extraordinary angle no other mission has ever matched. But it was designed, from its very first blueprint, to measure particles and magnetic fields, not to take pictures. It carried no imaging camera at all, and even if it somehow had, it was flying far too close to the sun, with no wide-angle optics of any kind, for the distant planets to have appeared as anything more than unresolvable points of light, utterly lost against the sun's own overwhelming glare. Other famous images that people sometimes mistake for a top-down view fall short in their own specific ways. Voyager 1's celebrated 1990 family portrait. The image that later inspired Carl Sagan's reflections on the pale blue dot was captured from roughly 40 astronomical units away, but it was taken from almost directly within the ecliptic plane itself, a shallow, edge-on angle, not a genuine bird's-eye view looking down. And in March 2025, the European Space Agency's solar orbiter delivered the first ever images of the sun's south pole, a genuine, historic milestone, captured from a modest angle of 15 degrees below the solar equator. But that mission photographed the sun's own pole directly. It remains deep within the inner solar system, nowhere near far enough out to frame the wider plane of the planets themselves. A dedicated mission specifically designed to deliver that missing photograph. Sometimes referred to in proposal documents as a solar polar imager or an out-of-ecliptic observer, has been seriously proposed more than once by more than one space agency. None has ever flown. The underlying propulsion requirements, even using the most advanced solar sail concepts currently under study, remain genuinely marginal, difficult to fund, and difficult to justify against competing mission priorities that, understandably, tend to favour destinations we can actually reach within a reasonable budget and a reasonable number of years. This is the final, defining discovery of tonight's exploration. We know, with extraordinary precision, exactly what our own solar system looks like from above. Earth's orbital velocity alone has been measured to 5 decimal places. Planetary positions can be confidently computed thousands of years into the past and thousands of years into the future using nothing but careful mathematics. And yet we have never actually looked at any of it that way. Not once. Every single diagram, every planetarium sequence, every textbook illustration you have ever seen of our own cosmic neighborhood, viewed from above, is a beautiful, mathematically exact drawing of a place no human eye and no human camera has ever actually visited. Since brute force propulsion could never pay the bill for a large plane change, and since a genuine photograph from above remains, for now, permanently out of reach, it's worth understanding the one real trick that does work. The same trick that got Ulysses to 80 degrees in the first place, and the closest thing humanity currently has to an actual solution. A gravity assist works by transferring momentum between a spacecraft and a planet, governed by nothing more exotic than Newton's third law. For every action, an equal and opposite reaction. because a planet like Jupiter is almost inconceivably more massive than any spacecraft, by a factor of roughly 10 to the 24th power. The spacecraft's own velocity can change dramatically during a close flyby, while the planet's own velocity shifts by an amount so infinitesimally small it's essentially impossible to ever measure directly. Here's how it actually works. A spacecraft falling toward a planet gains speed as it falls inward, and then loses precisely that same amount of speed again as it climbs back away. Measured entirely from the planet's own point of view, the encounter behaves like a perfectly elastic collision with no net change at all. But the planet itself isn't standing still. Jupiter, for instance, is moving around the Sun at roughly 13.07 kilometers per second. Adjust the flyby's precise geometry to send the spacecraft trailing behind Jupiter's own direction of travel, and you effectively subtract from the spacecraft's speed relative to the Sun. Send it ahead in Jupiter's leading direction instead, and you add to it. The energy involved has to come from somewhere, and it does. From Jupiter's own orbital motion around the Sun. Jupiter loses a genuinely tiny sliver of its own orbital energy during the encounter. So small, given its almost unimaginable mass advantage, that it will never be measurable by any instrument humanity could ever build. And the spacecraft gains something extraordinary in return. NASA's own technical materials describe this, with a certain dry accuracy, as adding or subtracting energy from a spacecraft's trajectory essentially for free, at least from the narrow standpoint of the spacecraft's own limited fuel budget. And crucially, this exact same trick can rotate a spacecraft's velocity vector, not just its speed, meaning it can genuinely change orbital inclination, angling a trajectory up out of the plane without spending a single additional drop of propellant to do it. This is precisely what Jupiter's gravity did to Ulysses in February 1992. It's a smaller scale version of the same trick that the Cassini mission used repeatedly at Saturn's moon Titan, gradually raising its own orbital inclination from nearly 0 degrees up to roughly 75, specifically so it could observe Saturn's magnificent rings from above and below, rather than only from directly within their own plane. For narration purposes, here's a simple way to picture the mechanism directly. Imagine standing perfectly still, holding a small ball, as a passing train brushes gently against it. Relative to the train itself, the ball arrives and departs at exactly the same speed. Nothing has changed from the train's own point of view. But relative to you, standing on the ground and watching, the ball has been genuinely redirected, and depending on the precise geometry of the encounter, either sped up or slowed down in the process. That, in essence, is a gravity assist. The catch, and it's a real one, is that gravity assists require the right planetary alignment, and you don't get to simply choose when that alignment occurs. You have to wait for the universe to hand it to you. Ulysses had to wait patiently for years until Jupiter drifted into precisely the right position in its own orbit. Voyager 2's famous Grand Tour of all 4 gas giants, Jupiter, Saturn, Uranus, and Neptune, visited in a single continuous mission using a careful chain of gravity assists, depended entirely on an outer planet alignment that occurs only once every roughly 175 years. Solar Orbiter, currently in flight, is using a patient, repeated sequence of Venus flybys to slowly, gradually tilt its own solar orbit, aiming for a heliographic latitude of roughly 33 degrees by the late 2020s. A genuinely impressive achievement, and still less than half of what Ulysses managed, more than 3 decades earlier, using a single decisive encounter with Jupiter. Gravity assists, in other words, are remarkably cheap in fuel. They are correspondingly, and often severely, expensive in patience. So where does that leave the actual dream? A real, camera-equipped spacecraft, genuinely positioned above the solar system's flat plane, finally capturing the photograph no one has ever taken? The honest answer, drawn from current mission engineering, is a short and genuinely difficult list of options. The first option is simply more of what already works. Additional gravity assists, chained together with real patience. Solar Orbiter is already demonstrating the near-term version of this approach, using repeated Venus flybys to slowly tilt its own orbit. A future, more ambitious mission could, in principle, chain together Venus, then Earth, then Jupiter, accumulating considerably more inclination than Solar Orbiter alone will ever reach. At the cost of very long total transit times and rigid, narrow launch window constraints dictated entirely by planetary alignment, rather than by anyone's actual preference or funding timeline. The second option is solar sails, a genuinely elegant idea using a large, thin, reflective membrane pushed continuously outward by the gentle pressure of sunlight itself. That pressure is tiny at Earth's distance from the Sun, something on the order of 9 micronewtons per square meter of sail. But unlike a rocket, it never runs out of propellant because it needs none at all. Over months and years of sustained, gentle pushing, a carefully designed sail can gradually spiral inward toward the Sun, and by tilting cleverly against the sunlight, accumulate genuine out-of-plane momentum over time. A concept called the Solar Polar Imager envisions exactly this. A sail-driven spacecraft eventually reaching a tight 0.48 astronomical unit orbit, inclined 75 degrees to the ecliptic. Arguably the most realistic near-future answer currently on the table to the question of finally getting a genuine camera above the plane. NASA's Solar Cruiser technology demonstrator has been working to prove out some of the underlying engineering this kind of mission would eventually require. The third option is ion, or electric, propulsion, considerably more fuel-efficient than any chemical rocket, with exhaust velocities up to roughly 50 kilometers per second, an order of magnitude better than traditional engines. The trade-off is thrust. Ion engines produce remarkably little force at any given moment, sometimes compared to roughly the weight of a single sheet of paper resting on a table here on Earth. NASA's Dawn mission, which used ion propulsion to visit and orbit both the asteroid Vesta and the dwarf planet Ceres, accumulated a total of roughly 11 kilometers per second of delta V, but only by thrusting almost continuously for years at a stretch. Applying the same underlying technology to a genuine out-of-ecliptic mission would work, in principle, but the total mission timeline would very likely stretch across multiple decades. And the fourth option is nuclear propulsion, either nuclear thermal or nuclear electric, which could, in principle, deliver both the high efficiency of ion engines and considerably more usable thrust than any solar sail could ever provide. But no operational deep space nuclear propulsion system has ever actually flown. Development programs, including NASA's more recent Draco project and the historical NERVA program from decades earlier, remain, as of this telling, confined to ground-based testing. The honest summary, drawn directly from current mission engineering, is this. With the technology that exists today, sending a genuinely camera-equipped spacecraft to a true bird's-eye view of the planetary orbits within any single human career's working lifetime simply isn't possible. Solar sails and carefully chained gravity assists can, together, deliver modest, genuinely useful heliolatitudes, but only at real, substantial cost in total mission time. A full, honest, bird's-eye photograph of our own solar system remains, at an absolute minimum, a multi-decade undertaking, one that no space agency, anywhere in the world, has yet formally committed the funding to actually attempt. This is not a story about failure, or about a task that will remain forever impossible. It's a story about a genuinely hard engineering problem, with a short list of promising but still unproven paths forward, none of which has yet been fully built, funded, and flown. The picture remains, for now, unphotographed. Not because nobody wants it, but because no one has yet found an affordable way to actually take it. Let's close, then, with the picture itself. Not as a photograph, because none exists, but as the extraordinarily precise, mathematically constructed image that generations of astronomers have carefully built in its place. We know what our own solar system looks like from above the way a blind person might know the layout of their own childhood home, by touch, by memory, by careful and repeated inference built up patiently over a lifetime. Precisely, exhaustively, but never once by direct sight. Every simulated view from above you have ever encountered is a rendering, built entirely from measurements taken from within the plane itself, extrapolated outward using Newton's laws and centuries of refined orbital mechanics. If you could somehow stand above the solar system's north pole and simply look down, current models predict, with real confidence, exactly what you would see. The sun itself, a brilliant point of light, larger and steadier than any star, but still fundamentally star-like from that kind of distance. Mercury and Venus tracing tight, fast little circles nearest the sun. Earth, just beyond them, a small point of blue and white. Mars, a slightly larger loop, tinted red-brown. Then a wide, comparatively empty gap. The asteroid belt, appearing not as some dense, solid ring the way it's so often drawn in illustrations, but as a genuinely sparse, faint haze, the overwhelming majority of its individual bodies simply too small to ever resolve, even from directly above. Beyond that, Jupiter, large and slow-moving, unmistakable. Saturn further out still, its magnificent rings tilted at some angle relative to your particular vantage point. Uranus and Neptune, farther out again, moving so slowly along their orbits that across an entire human lifetime, they would barely appear to shift position at all. And beyond even them, the diffuse, scattered cloud of the Kuiper belt. Pluto tilted a full 17 degrees above the shared plane, along with countless other small, icy worlds, each inclined at its own particular angle in every direction. And the whole system, taken together, would look almost impossibly flat. Here's a way to genuinely feel that proportion. If the outer edge of Neptune's orbit was scaled down to match the outer rim of a standard compact disk, roughly 12 centimeters across, the total vertical spread of all 8 major planets' orbits, measured above and below the solar system's true invariable plane, would be thinner than the CD itself. Not a noticeable gap. Not a visible wobble. A margin smaller than the physical thickness of the disk you'd be holding in your own hand. And here is the quiet realization worth carrying with you as tonight closes. No human-made object has ever actually seen this. We know it's there. We have measured it into existence with a precision that would have seemed like magic to any earlier generation of astronomers. We can compute planetary positions confidently across thousands of years in either direction. But no camera has ever hovered directly above the disk and simply looked down at it. Ulysses came closer than any other mission in history ever has. A small, silent spacecraft, deactivated since 2009, still coasting somewhere out there along its own long, looping solar-polar orbit, having flown high above the sun 3 separate times, having never once turned around to photograph the flat, familiar plane it had left so far behind. Every view from above you have ever encountered. Every animation, every diagram in every textbook, every planetarium sequence you've ever sat through, is a beautiful, careful, mathematically exact drawing of a place no human eye has ever actually visited. The most familiar portrait of our own solar system is also, quietly, its most imagined one. There is something genuinely worth sitting with here, now that we've walked all the way through this story. We tend to assume that knowledge requires sight, that to truly know a place, we must, at some point, actually look at it directly. And yet the solar system we live inside, the specific flat disk of worlds we've spent our entire existence as a species orbiting through, the precise shape and structure of our own cosmic address, has been reconstructed almost entirely without ever being seen from outside itself. Every single measurement that built the picture was taken from within the plane. Every equation, every careful triangulation, every patient decade of astronomical observation, gathered by scientists who were themselves permanently embedded inside the very structure they were trying to describe. And it worked. It worked extraordinarily well. We know Earth's orbital velocity to 5 decimal places. We can predict where every major planet will sit in the sky, centuries from now, or centuries in the past, using nothing but mathematics developed by people who never once left the plane themselves. This is, when you actually stop to consider it, one of the more remarkable achievements in the entire history of human thought. An accurate, detailed, trustworthy portrait of an entire structure, built patiently by observers who could never step outside it to check their own work directly. There's a kind of humility embedded in that fact, and a kind of quiet confidence too. Humility, because it reminds us that even our most familiar, most confidently illustrated scientific images, the ones we draw for children in their very first astronomy lessons, often rest on inference rather than direct sight. Confidence, because that inference has proven, again and again, across centuries of careful checking, to be extraordinarily reliable. The picture in the textbook is not a photograph, but it is not a guess either. It is something rarer and, in its own particular way, more impressive than either of those. A portrait built entirely out of patient reasoning, verified repeatedly against reality, without ever once requiring the vantage point it actually describes. We are, perhaps, a little like the very planets we're trying to picture. Permanently embedded within a plane we did not choose, inheriting a velocity, a direction, and a perspective we never personally selected, simply by virtue of being born on the third rock from a star that happens to sit at the center of it all. And from deep inside that plane, looking only sideways, never once from above, we have still somehow managed to reconstruct, with genuine, verifiable precision, the true shape of the very thing we're embedded within. That is not a small accomplishment. It might, in fact, be one of the more genuinely remarkable things our species has ever managed to do. Picture it, one last time, before we close. Somewhere out there right now, well beyond the orbit of Jupiter, a small, silent, powerless spacecraft continues coasting along its own long, looping, solar-polar orbit. The exact same orbit Jupiter's gravity bent it into, more than 3 decades ago, on a single afternoon in February 1992. Ulysses. Deactivated since 2009, its radioisotope power finally too faint to sustain any further operations, but still moving, still following the precise physical laws that carried it to a vantage point no other human-made object has ever occupied. 80 degrees above the sun's own equator, higher, in the one dimension that actually matters for tonight's story, than any other spacecraft in the entire history of our species. And it never turned around. It never had a camera to turn around with. The one machine that ever genuinely escaped the flat plane every planet, every asteroid, and every prior spacecraft had always obediently stayed within, looked outward at everything except the very thing that made its journey so remarkable in the first place. It felt the solar wind streaming from the sun's poles. It measured a weakening magnetic field and captured an entire 11-year reversal and found interstellar dust far more abundant than anyone had expected. But it never looked back and took the picture. Somewhere, in some future decade, if a solar sail finally proves itself, or if a patient enough chain of gravity assists is finally funded, or if some entirely new propulsion technology finally makes the delta V problem tractable, a different spacecraft will eventually go where Ulysses went, carrying instruments Ulysses never had. And for the first time in the entire history of our species, a camera will look back down at the flat, familiar plane containing every planet we have ever visited, every moon we have ever photographed up close, every human being who has ever lived. And it will finally see, directly, with its own lens, the actual shape that centuries of careful, patient, sideways-facing mathematics have always insisted was there. Until that day arrives, the picture remains exactly what it has always been, the most familiar image in all of astronomy, and also, quietly, the one photograph that has never actually been taken. Tonight we explored why it's impossible to go up in the solar system. And what we found was not a single obstacle, but a chain of them, each one connected directly to the last. We found that up itself has no universal meaning in space, that even in low Earth orbit, gravity never actually disappears, and the human body's own sense of direction collapses within about 48 hours of continuous free fall, long before we ever try to apply the word to something as vast as an entire solar system. We found that every planet, moon, and major asteroid orbits within an almost impossibly thin shared disk, a structure inherited directly from the spinning cloud of gas and dust that built our solar system 4.6 billion years ago, with the 4 giant planets alone carrying 98% of its entire angular momentum. We found that exactly one spacecraft out of hundreds successfully launched across more than 60 years of spaceflight has ever genuinely left that plane, and that it could only do so by borrowing momentum directly from Jupiter's own gravity, because no rocket ever built could generate anywhere near enough delta V to make the journey through propulsion alone. We found a rocket equation and a plane change formula that together make changing direction in space dramatically more expensive than simply travelling farther or faster. Expensive enough that a full 90-degree turn out of the ecliptic would require roughly 15 tons of fuel for every single kilogram of spacecraft delivered. And we found, at the centre of it all, the quiet, genuinely striking fact that no human being and no human-made camera has ever actually seen our own solar system from above. Every familiar image is a mathematical construction, extraordinarily precise, thoroughly verified, and entirely unphotographed. None of this is a story about failure. It's a story about exactly how much energy, patience, and precisely engineered borrowed momentum it actually takes to change direction at the scale of an entire solar system, and about how much we have still managed to understand about our own home, using nothing but careful mathematics and centuries of patient observation, from a vantage point that has never once left the plane. We live our entire lives, and our entire species' entire history, embedded inside a disk thinner, relative to its width, than the crust of a pizza. We have never looked at it from outside, and yet we know, with real confidence, precisely what it looks like, reconstructed, patiently, sideways, by generations of people who never once got to check their own work by simply looking down. Sleep well tonight, inside a plane you have never left, on a world orbiting at nearly 30 kilometers every second, carried along a path so flat and so precisely understood that we can trace it backward and forward across thousands of years, even though no eye, ever, has looked down and actually seen it. Good night, and rest well under the stars, and within the quiet, patient, unphotographed shape of the only home any of us has ever known.